In this video, we study the famous consensus problem in distributed systems. Specifically, we consider algorithms that aim to reach consensus deterministically, that is, without the use of randomization. As far as communication is concerned, we consider the standard model where distributed processes, called nodes, communicate by exchanging messages. We assume that all messages arrive within a certain bounded time, which is often called the synchronous communication model. In this model, we can think of algorithms running in synchronized rounds where every message is sent and received in a particular round. The different nodes have some local state. For the sake of simplicity, we assume that the local state is simply a natural number. The goal is to agree on a single value. Let's start by defining the consensus problem more formally. We say that an algorithm solves the consensus problem if it has the following three properties. The first property is called agreement, which says that all nodes must decide on the same value whenever they decide. The second property is called validity. There are different definitions of validity. In this video, we use the definition that if all nodes have the same input value, then the nodes must decide on this value. Lastly, the third property is called termination, which says that all nodes must eventually decide on a value. How can nodes reach agreement? Let's start with a simple algorithm. In this algorithm, every node simply sends its value to all other nodes and receives all other values. Since communication is synchronous, every node knows when all messages must have arrived. The nodes then simply decide on the smallest received value. Do you see a problem with this algorithm? You can pause the video here to think about it. We will continue here shortly. Did you discover the problem? Let's assume we have 5 nodes with the given input values. When sending their values to other nodes, it is possible that a node crashes in the process. In the unlucky scenario here, the node with the smallest value crashed, but not before it managed to send its value to one other node. This node then decides on the smallest value, but all other nodes do not. How can we fix this? The problem is clearly that there was a node failure during the round. If we assume that at most f nodes may fail, we can run the following algorithm. For f+1 consecutive rounds, each node broadcasts its value, collects all other values, and always sets its value to the smallest received value. At the end, it decides on its own value. Does this algorithm work? Let's look at an example. We assume that there can be at most 3 failures. In this execution, the node with the smallest value didn't manage to send any messages before crashing in the first round. The node with the second smallest value crashed as well, but it managed to send a message to one other node. In the second round, this node also crashes, but not before it sends its value to the node at the bottom. In the third round, there cannot be any crashes anymore because 3 nodes have already crashed, so the node at the top learns about the second smallest value. Nothing changes in round 4, so both remaining nodes agree on the same value. Why does the algorithm work? The reason is that in f+1 rounds, there must be at least one round where no node fails. In this round, all nodes adopt the same minimum value. It is easy to see that the nodes do not change their value anymore in any future rounds. So, we can solve the consensus problem for any number of failures by executing one more round than the maximum number of failures. An obvious question is whether we can do better. Is it possible to solve the consensus problem in fewer than f+1 rounds? In the following, we will show that this is, in fact, not possible. If all inputs are 0, recall that the validity property states that the agreed-upon value at the end must be 0. We will construct the proof in such a way that validity can be violated if an algorithm runs for fewer than f+1 rounds. The main ingredient of the proof is a clever use of indistinguishable executions. Consider the following 2-round execution of an algorithm. If we focus our attention on the node in the middle, it is not affected by the message that the node at the top sends to the node at the bottom in round 2. So, if we drop it, the node in the middle will still have the same output. We say that this execution is equivalent to the previous execution with respect to the node in the middle. If we focus on the node at the bottom, we can introduce a message from the top node to the node in the middle in round 2, which leads to an execution that is indistinguishable for the node at the bottom. We can also make a node crash. In this scenario, the node in the middle crashed before sending any messages in round 2. This execution is indistinguishable for the node at the bottom because it did not receive a message from the node in the middle anyway. More generally, we say that two executions are equivalent if they are indistinguishable for some node. The crucial observation is that the output of all nodes must remain the same in equivalent executions. The reason is that there is at least one node that cannot distinguish between the two executions, so this node will not change its output. So, agreement would be violated if other nodes change their output. Formally, we are now going to show that the following theorem holds. If there can be at most f-crash failures, any deterministic consensus algorithm requires at least f+1 rounds even if communication is synchronous. Let's start with f=1. We assume that all inputs are 0, which entails that all outputs must also be 0. If we focus on the first node from the top, it is easy to see that we get an equivalent execution by removing the messages marked with arrows. So, we crash the node after sending its message to the node at the top. Let's now focus on the node at the bottom. This node will not change its output whether or not the message from the node in the middle is sent to the first node. We can conclude that we get an equivalent execution by dropping this message too. Since the node crashes right at the start of the execution, its input value might as well have been 1. If we again focus on the node at the bottom, it will not change its output if the node in the middle actually crashes after sending a message to the first node. If we focus on the first node again, this node will not change its output if the node in the middle crashes after sending the other messages. But this execution is equivalent to the middle node crashing after the first round. Since it doesn't send any messages anymore at this stage, the execution is equivalent to the execution where this node doesn't crash at all. So, we manage to get an equivalent execution without any failures where the input of one node is flipped from 0 to 1. We can now repeat the same steps with the third node, getting an equivalent execution where its input is flipped to 1. Lastly, we repeat the steps once more to flip the input bit of the first node. We now have an equivalent execution where all inputs are 1 and all nodes still output 0, which violates the validity property. We have now shown that a single round is not sufficient to deal with one failure. Let's see how we can apply the same techniques to show that 2 rounds are not enough if there can be 2 failures. First, we focus on the second round. We can use the same sequence of steps as for f=1 to get to an equivalent execution where node number 4 crashes at the start of round 2. This is equivalent to node 4 crashing in round 1 after sending its messages. We can drop the message that it sends to itself before crashing without a problem. While we cannot just remove the message sent to node 3 because node 3 could then change its behavior in round 2 and inform the other nodes, we can use the same sequence of steps as for f=1 again to get an equivalent execution where node 3 crashes at the beginning of round 2. Now we can remove the message because messages between failed nodes do not affect the other nodes. We can then use the same sequence again to get an equivalent execution where node 3 does not fail. We can repeat these steps to remove the message to node 2. First, we make node 2 crash at the beginning of round 2, then we remove the message and then use the same steps again so that we get an equivalent execution where node 2 doesn't crash. Removing the last message to node 1 works the same way. First, we make node 1 crash at the beginning of round 2, we remove the message and then we make node 1 not crash at all. We can get an equivalent execution by changing the input of node 4 to 1. At this stage, we perform the same steps backwards. We make node 3 crash at the beginning of round 2, add the message from node 4 to node 3, and then make node 3 not crash again. Next, we make node 2 crash at the beginning of round 2, add the message from node 4 to node 2, and then make node 2 not crash again. Lastly, we make node 1 crash at the beginning of round 2, add the message from node 4 to node 1 and then make node 1 not crash again. This execution, where node 4 crashes after sending all messages in round 1, is equivalent to an execution where node 4 crashes at the beginning of round 2. We can then transform this execution again to an execution where node 4 doesn't crash at all. We can then repeat all these steps for node 3, flipping its input from 0 to 1, and then repeat the same thing for node 2 and, finally, node 1. In doing so, we end up with an equivalent execution where all inputs are 1. Since the output is still 0, the validity property is again violated. These steps can be recursively applied to any number f, which then proves that f rounds are insufficient to solve the consensus problem if there can be up to f failures. Let's summarize what we've learned. We studied the consensus problem with the three properties agreement, validity, and termination. We saw that the problem can be solved using a simple algorithm in f+1 rounds. We then showed that it is not possible to solve the consensus problem using a deterministic algorithm in f rounds, that is, any algorithm requires at least f+1 rounds. Thanks for watching.